Thank you very much for joining us for this this month's WeRobotics webinar series, which will be focusing on marine robotics. If you've joined our seminar series in the past and are familiar with WeRobotics, you'll know that we work across a number of different robotic solutions, not just the aerial variety, so-called drones and UAVs, but are very keen on expanding the use of these technologies, robotic solutions, to include marine robotics or surface water robotics, underwater robotics, as well as ground-based terrestrial rover robotics, and exploring exactly how these technologies can be used in a wide range of humanitarian and development settings, as well as environmental and public health. So we're really fortunate to have Ryan join us, who's been doing this for literally decades on the marine robotics side, has a lot of practical, technical experience, and who personally has provided us within the executive leadership of WeRobotics with some really invaluable guidance on opportunities, as well as some of the challenges we need to keep in mind in terms of using this very exciting area of robotics for social good. So what we're going to have is Ryan's going to kick us off with an overview of the existing technologies and capabilities. And Ulyana was going to join us to present her work in the Himalaya, but unfortunately she just got pulled into a last-minute meeting with her team collaborators at NASA. So she sends her deepest apologies and has invited me to just fill in for her. I've presented her work before, so I'm very up to speed in the good work that she's been doing. So I'll follow up then with a quick overview of her work. So with that, Ryan, thanks again for joining. We're really thrilled to have you here, and over to you.
Well, thank you for having me. I really appreciate the opportunity to talk with everybody and present on this topic. What I put together are a few slides here just giving kind of a basic overview of underwater vehicles, aquatic vehicles really in general, and what that space encompasses in part of the technology that exists that's out there for platforms. And then I'll finish off with a little bit of work that I've done and kind of talk about where we're going, what's being enabled, and what we can do in the aquatic space with robots today. So just to kind of give you a little bit of a background, I run the Robotic Gnome Lab at Fort Lewis College, and I'm primarily interested in looking at robotic perception, conceptualization, planning, and long-term navigation, so persistent environmental monitoring with robots in challenging, dynamic, and unsafe environments. That involves a little bit of computer vision, that involves a lot of path planning, deliberation, decision making, machine learning, all kind of put together in a very dynamic and complex space. So if it's underwater, on top of the water, or aquatic, I really like to try to tackle it. So just to kind of give a start, I'll talk about what platforms exist, and these are pretty much commercial, off the shelf these days, ranging from about $50,000 up to about $500,000 US, and anybody can go and buy them. The cool stuff I'll get into a little bit later about what we actually do with them. So we usually look at underwater vehicles or aquatic vehicles as, what's the level of autonomy, how long do they last, how deep do they go, are they configurable, reconfigurable, modular, what kind of software do they run, is it proprietary or open source, and how controllable are they, what kind of maneuvers can they do. So when you look at kind of the autonomy space, you really look at power, communication, and tether, starting kind of with your ROVs, the remotely operated vehicles, which are kind of shown up over there on the right hand side. Oops, oh no, what happened there? And then you look at kind of what communication they have, and the more autonomy that a robot has, the less communication it's going to have. Therefore, it's also going to have a little bit more power as you move through, giving it more autonomy so it can actually be out in the environment a little bit longer. You're going to also have to have a lot of deliberation on board, decision making, and so you're going to need that extra power. When you look at kind of the software, you go from the remotely operated vehicle with manual control to a basic kind of GPS waypoint navigation, which I will argue is not autonomous, all the way up through in situ decision making and full autonomy on board. So kind of from top to bottom there in the software, we rise through autonomy that way. As for kind of the vehicles themselves, you need propulsion and sensing basically to move through the water. The traditional propeller-driven propulsion systems obviously take a heck of a lot more power than some of the more sustainable methods using buoyancy or wave power or solar to generate motion through the water. And we'll see a couple examples a little bit later. Sensors are kind of your big guys in power consumption as well. You know, when you start running sonar or Doppler velocity loggers or things like that, you can eat up a bunch of power there. But for the most part, water quality sensors, GPS compasses, that's really come down in price and power consumption. We can actually do quite a bit, quite cheaply as far as that. There's a lot of talk in autonomous vehicles, and especially in the aquatic environment, based on communication. When do you communicate? It's very power expensive to communicate underwater, very dollar expensive to communicate by satellite above water. So how do we do this, especially for platforms that are kind of pelagic or blue water platforms? You know, they're out for months at a time in the middle of the ocean. What's the best way to give them the best opportunity to communicate? That also comes into localization. Basically, you need to communicate to localize out there in some sense or form. So how do we actually do that? And then there's a lot of development now in the computing resources on board, and I'll talk a little bit about that later. So now I'm going to kind of go into a few examples on each of the vehicles that are kind of standard or state-of-the-art out there right now. So ROVs, which are remotely operated vehicles, AUVs are autonomous underwater vehicles, there's autonomous gliders, there's ASVs, which are autonomous surface vehicles, there's a wave glider platform made by Liquid Robotics, which is a very specialized platform, and a couple miscellaneous items I'll hit on. So when we talk about remotely operated vehicles, these go from basically the little sea perch made out of some PVC pipe and swimming pools that are done by high school and undergraduate students, all the way to the big working class ROVs that can go down to 4,000 or 5,000 meters. You know, Embari has some of those, Woods Hole has a few of those, NOAA has some of those. These are tethered, they're operated from large ships. There are some autonomous capabilities like autonomous hovering or station keeping while you're trying to manipulate some arms or take pictures or something like that. And basically these are just big, huge pickup truck type rigs that you just slap a whole bunch of sensors on and throw them to the bottom of the ocean and go try to do some work. Some of the new work that's going on right now is on manipulation tasks underwater. So putting high degree of freedom arms and manipulators onto these ROVs and doing tasks underwater, valve turning, welding, you know, changing out instruments that are down at subsea research stations and things like that. You know, one of the most highly prolific ones is called the VideoRay. It's a consumer-based model. These things run about $15,000. They've got a 100-meter tether on them usually, a couple of thrusters, and basically just a few thrusters built around a camera is really all it is. And these have been used to do a lot of pipeline surveys, map up a whole lot of caves and things like that. They're kind of the first real consumer ROV, if you will. They came out probably 15 years ago and have been developed and redeveloped over the years and are actually a pretty darn good product. Then you can go up to their big Ventana, which is Embari's vehicle, and this is a big guy, 8 kilowatts of power. Basically, you can go down to about 2,000 meters, but you can see you need a big J crane on the ship to even get that up and down. You know, really an immense rig. there's a whole station on the ship just to run this vehicle, and probably 3 pilots that it takes to drive this guy around. When you start looking at autonomous underwater vehicles, you cut the tether on those ROVs, and all of a sudden things have to shrink down quite a bit, basically to reduce drag and maximize or minimize power consumption, so maximize deployment. They usually have some kind of GPS or waypoint navigation when they're on the surface, and then dive down and use any host of control or path planning or mission planning techniques to navigate through the ocean. There's a whole bunch of different options for computing, onboard and offboard, communication reliant on there. But you can see there's the primary shape of these guys is about a 25, 26 centimeter cylinder. And these cylinders can get 3 to 4 meters in length. The typical length is about 1.6 to 2 meters long, and like I say, about 25 to 30 centimeters in diameter. Remus is probably the most prolific autonomous underwater vehicle that was made by Kongsberg, and now I believe they're owned by iRobot. And they've been kind of being bought up across the years here. They have a bunch of different models. The deepest one goes down to about 6,000 meters. Can be out for about 22 hours. So when you look at a propeller type vehicle, this is pretty much the max duration for any propeller type vehicle that you'd see out there is about a day. It can go about 3 meters a second. And basically this one does the deep ones do a combination of buoyancy driven and propeller driven motion through the water. That's why they can actually stay out so long. There's a Hanu Singh out of Woods Hole developed what they call the Seabed AUV. It's a kind of a dual cylinder type vehicle. This is one that's really used for going very slow, goes down to about 2,000 meters, but really, really good for precision computer vision and underwater photography. They've done some really good seafloor imaging over a lot of coral reefs. I worked with a couple of these when I was down in Australia. University of Sydney has a few of these. And basically mapping fish habitats is really what you're looking at there. Really slow, does really good visual slam. But has 6 or 7 cameras on it that are really, really powerful, and she'll only stay down for about 4 to 6 hours. 6 is really pushing it with this guy. Let's see. Then if you look at autonomous gliders, these are buoyancy-driven vehicles. If you haven't seen these before, basically what they are is you take a cylinder and you make it about as neutrally buoyant as you can. There's one I worked with in the upper right there when I was at the University of Southern California. Take about a $50 piece and set it on top of that, and that thing will sink. So it's about 10 grams positively buoyant. What happens is you have a little vacuum pump. You suck water into the nose, and it becomes negatively buoyant, so it literally sinks. This guy will sink down to a threshold depth that it sets with that you set with a inside. And then it basically does these what we call yo-yo trajectories. You set a lower and upper bound, and it does vertical profiling. Once it gets down to your threshold depth, the pump pushes the water out, it becomes positively buoyant, and the buoyancy force pushes this back up to the surface. The wings on the side are there to convert the vertical motion into horizontal motion. However, this vehicle actually will go in a horizontal motion without the wings, although not very efficiently. These things nominally last about 30 days on 278 C-cell batteries. Trust me, I have changed those a few times. Really robust platform. They've been run for many, many years, and they've actually crossed the Atlantic Ocean. Oscar Schofield out of Rutgers University has a whole fleet of these. I think he's up to about 50 now, and he has crossed the Atlantic with them with extended payloads, extended batteries. But these are really good for persistent long-term monitoring and kind of catching features of interest in a body of water that you're not sure when they might occur. But very prolific platform used quite widely.